Okay, so that is where we call torque. So when it is a torque, when the centroid position did not move, or the deformation, not all, and the deformation is by twisting. So you will ask me, Eugene, what do I mean by twisting? Okay. So if we were to look at the centroid, I'm going to draw the centroid big now. Okay, we look at the centroid. Then we'll change to green. This is our centroid. Okay. So if this is our centroid, and this is our point A, because of the twisting, point A will move to what? A prime. Okay, so the point A, the dot, this cross over here, did not move. It only what? It only rotate. All right, it only what? Rotate from A to A prime. So this is what? So hold on, let me draw this figure better. I do apologize. Okay, this is center. Okay, so this is point A. This is the original point A, and then due to the torque, okay, you get A prime is due to the torque. So what you see from A to A prime, you have what we call an angle over here, angle over here, and this angle over here we call gamma. Okay, it's shear. Okay, it's a twist. Okay, that is known as gamma. So this is where we have a torque. Okay, so what are the things? So let's quickly sum. I know it's a lot over here. Okay, it's a lot over here. So what do we have? Okay, so first thing, step number one, we have to identify our global transformation. Okay, then we have to identify the centroid. Now you can see how important is a centroid, right? The centroid can tell us whether it's a bending moment or is it a torque, right? Then after that, do not analyze the dot and crosses, right? And what is more important is this, right? What we have learned is when the applied force is parallel to the centroid, the perpendicular distance is between the applied force to the what? Centroid, right? So when the applied force is perpendicular to the centroid, then the perpendicular distance is between the applied force to the element, okay? And then again, all is relative to the centroid. So when it's a moment, the deformation pattern for the centroid is what? Again, I will highlight over here centroid. Okay, centroid. Okay, when it's a moment, the deformation pattern is either a smiling face or sad face. When there's a torque, the centroid position did not change, and the deformation is by what? Rotation or by twisting. Okay, right. So I want to like improve your like confidence. Okay, we are going to look at other problems. Okay, we're going to look at other. So for now, I'm not going to calculate stresses yet. I want to see. I want to go to more examples to see if you could understand the concept when it's in a moment, when it's in a torque, so on and so forth. Okay, and I'm going to apply the procedure that I've written out. Okay, so let's look at example number 2 now. Okay, so I'm going to get this example over here. Right. Okay. So you see a structure over here, right? Again, a lot of information are given, right? You can see over here, and the transformation is given, so we know that this is our x, this is our y, and this is our z. So all this is given, which is good news. Okay, so the next thing we are going to do is we are going to look in the xy plane. Okay, we're going to look in the xy plane. So I'm going to sketch the structure in the xy plane. So this is our x. Remember I told you, right? 3D problem solving on a paper has to be 2D. Then you won't make any mistake. So this is your x, and this is your y, and then we know that this is our rotation about z. Okay, so the point of interest is element what? Element h. Okay, so I'm just going to sketch where element h is. So before we go on, we are going to sketch our centroid. Okay, the centroid relative to the element. So the centroid relative to the element is here. Okay, so this is what we call our centroid. Okay, so at that view, so I'm going to sketch element h. So this is 3. It's just a sketch. Wrong. Should not use this card. Okay, and then we have a distance over here. So if we were to calculate the distance, okay, so we know that we have this distance over here. We have this distance over here, right? Hold on. It looks kind of weird. So this is our distance over here, and this is our distance over here, and that distance is what? So this is 30 degrees. So sine 30. So this is 4. This is 6.9. 928. Okay, so this is 4. I'm going to draw 4. Okay. Okay, so this is our 4. And then we have a small bit over here. Right, we have another small bit over here. Again, this is just a sketch, okay, of 1. Okay. And then we have a force coming down. This is our P, right? So we're going to draw our element. Okay, so over here, this is our element over here. This is our element H. And then we draw our centroid. Right, we draw our centroid. Okay, we draw centroid. So we know that we have a Vy. So there's only one force only. We know that we have a Vy that is equal to P, right? A shear force in Y that's equal to P. And we know that for element H, right? And for element H, the shear stress is equal to 0, right? So some of you may say, why I mentioned that the shear stress will be equal to 0 over here at element H. So if we look at the formula, the shear stress is equal to Vy over Izz Qz divided by T. And if we look at the cross-section view, okay, if I'm going to draw the cross-section view of element at where element H is located, okay, so what we are looking at is now this is our Y and this is our Z. We know there's a load P coming down here. And over here, this is our element H. And if we were to recall the shear stress distribution, right? So if we look at the shear stress distribution, let me try to move this. Okay, so I have, come on. Right, so if I were to sketch the shear stress distribution, right, you guys, oh yeah, this looks familiar now. If we want to sketch the shear stress distribution, right? So this is our shear stress. This is our shear stress. This is our Y displacement. We know that the shear stress will distribute like this. So at element H, the shear stress will be equal to what? 0, right? So that's where this topic, you have to recall what you have learned since week 1. Right, now we are combining everything together already, right? We are combining normal stresses, shearing stresses all into now one now. Okay, right. Then from here, we know that there's a moment in the Z direction, right? We know that there's a moment, right? There's a moment in the Z direction, right? So what you can see now, the force is perpendicular to the centroid, right? So this is our centroid. So we know that the force is perpendicular to the centroid, right? So P, the moment P, right, is towards to the element. Okay. So now we have to find the distance from here to here. Okay. So if you look at this, so it's equal to 3 plus 1. Okay, 3 plus 1. Okay. So this will be equal to 4p. Okay, so this is equal to 4p pound inch, and it's going to rotate in this direction. So now this is our moment in Z, right? And then it's going to be compression, and it's going to be what? Tensile over here. So based on moment in Z, element H is going to be what? Tensile. Okay. Okay. So one view is done. Okay. Next, we are going to look at the other view now. So the next view that we are going to look at is on the YZ plane. Okay. So next we are going to look at the YZ plane. Right. So we are going to look at YZ plane. So this is Y, this is Z, and this is our rotation X, right? Then we have, I'm just going to sketch this out, okay? So we have our shaft. This is where our element H is. And then more importantly, this is our centroid, right? Then at 30 degrees, at 30 degrees, right? We have a applied force coming down, P, right? So for this case, we know that there's a distance, there's a perpendicular distance over here. And we did calculate this perpendicular distance, right? So this perpendicular distance is equal to 6 point. So it's cos 30 times 8, 6.928. Okay, 6.928. So now let me ask you now, right? That is where our centroid is. When P come down, right, the chain line is going to deform. It's going to deform like this. Okay, it's going to deform like this. The red one is deformation. Okay, it's going to deform like this. Right? But the green dot is still at the same point because it's fixed to the wall. So is it a torque or a moment? So for this case, the green dot is not a smiling face or sad face at the same place. So that is where we classify this as a torque. Yes or no? So now you can write this down, that torque in the x direction is equal to 6.928 multiplied by P. Okay. And for element H, we know that there's going to be a torque. The shear stress is equal to Tx multiplied by radius divided by J. It's not going to be 0. There's going to be a value. Okay. So once you start obeying the rules, this does not look difficult. Okay, but you have to do quite a bit of practice. Okay, so what I'm going to do now, we're going to take a 5 minutes break. We come back at 8:15.